Mic on and everything? Okay. So, like you said, my name is Christopher Swenson. I currently work for Google, although this talk has nothing to do with my work at Google. This is just, Sage is something I care about in my spare time, and I'm a part-time contributor. So I thought I'd give this talk to sort of raise awareness on what Sage is and how awesome it is. I love Sage. I'm a huge fan. So let's talk about Sage. So how many here have actually used Sage? Just a handful, or okay, or even like just thought this would be cool because they love math, maybe? Anyone like math? All right, good. So Sage is all about math. So originally, Sage stood for Software for Algebra and Geometry Experimentation, although some people also say Algebraic Geometry Experimentation, but they decided to get rid of that and they just call it Sage now. It was started by William Stein in 2005. He has written several articles on exactly why he created this, and I encourage you to look at his blog. Just Google for William Stein and you'll find it, if you're interested in the deep history of why Sage exists. But otherwise, I'm going to sort of ignore the origins and just go on. So what is Sage exactly? So it's meant to be a totally free, open source, sort of re-implementation of all the good parts of Magma, Mathematica, MATLAB, Maple, all those M words, you know, in Python. So I guess to me, what Sage is really about is it's about being, you know, having all these great math tools at your fingertips, but without being bogged down with all the cruddy details of their programming languages they invented a million years ago, right? Like, I don't know if you've ever used like Mathematica or MATLAB, but they are just burdened by these awful languages that you have to program in order to access these really great tools they give you. You know, MATLAB has this great numerical processing framework, and Mathematica has really great, you know, graphing and, you know, symbolic manipulation work, but you have to write it in Mathematica to use it, right? And that's just really unfortunate. And so William Stein, part of his two main problems were that, for one, those languages are terrible, and Python is a great language, so why don't we just use that? And two is that all of these implementations are also closed source. You couldn't look into the box to see exactly what kind of awesome things were going on. Should type more. You couldn't look into the box to see what they were actually doing to implement any of their interesting algorithms. And this really goes against the spirit of math in general. Math has been always a very open sort of science, right? Where, you know, you publish papers and people understand, you know, what you're doing. You don't do things behind closed doors. It's also worth noting Scytheon was sort of a sister project to Sage. So I'm sure that many of you have probably heard of Scytheon at least. It's very popular. I think there are other talks that talk about Scytheon as well. But it was actually developed as part of Sage. It was a spin-off of Pyrex that they started developing for Sage, and then eventually spun off whenever they realized it was actually, you know, popular outside of Sage as well. And I like to think of Sage as having a motto of as easy as Python, right? So I think a few things about like some of the pluses and minuses, and then I'll go into a demo. So what is Sage about, and what isn't it about? So it is about being completely free and open source. It's about being comprehensive. It encompasses, you know, basically everything they could think of, you know, to throw into it as well. You know, it's got the entire kitchen sink, and you'll sort of see what I mean. It's growing, so they have 100 developers roughly, probably about, you know, a quarter of them are active in the community at any given time. They sort of fluctuate exactly who's working on what at the moment, but, you know, it's got a fairly strong community. It's super easy to program in. This is the biggest thing I think of. You can either program it via the command line, which is the sort of standard Python, you know, interface, or via a graphical notebook, which was a very unique feature, but recently I think other players have come into that as well, such as IPython. The two most important features to me are object-oriented, and really the tab completion of IPython and the Sage notebook are incredibly powerful. The object-oriented is important because, again, if you've used like Mathematica or MATLAB, they're almost inherently un-object-oriented, right? There's, you know, almost no sense of objects, but math is a very object-oriented sort of paradigm, right? You have objects, you have sets, you have elements of those sets, and you do things with them, and that's sort of almost how object-oriented programming came about. So it's natural, I think, to think of math in terms of objects, and that's exactly how Sage treats it. And also, anything that Sage knows its own limitations, and it happily will call other programs to solve its problems. It integrates in, probably a dozen or a couple dozen different math packages like Gap and Maxima to do all sorts of heavy lifting that maybe they don't want to spend all their time re-implementing. And so they design interfaces to these. So what isn't it, though? It's not going to be faster than Mathematica and MATLAB and Magma in every single way possible. This just isn't reasonable. There's been a ton of work that's been put into those, and they can't easily just reinvent that in a couple of years with a handful of developers. It's also not slowed down by Python is another important part. This is part of why they use Scytheon, why they developed so much into Scytheon, is they wanted to make sure that they weren't bogged down by the fact that they're running in this really great language. And so that's what, and it's also not as well known yet as I think it should be, but hoping to change that through talks like this and, by its growing maturity. So I think without further ado, I'm just going to launch into demo mode now and just show off Sage, because I think it's great to talk about it, but I'm just going to launch into the Sage notebook now and do things that way. So this seems to not be in. There we go. So the Sage notebook sort of looks like this. And actually, before I actually even do this, let's talk. You can actually start up a Sage notebook yourself. Sorry, sagenb.org. And you don't even have to install anything to use Sage. This is actually, I think, one of the coolest features, assuming the internet works today, which of course it isn't. But anyways, you could take my word for it. If you go to sagenb.org, you can just essentially click a button and start up your own Sage worksheet that you can play around with and experiment with without installing anything. Okay, here it is. So I could sign into, no one really wants to use a username and password, so just sign in with, one of these billions of accounts you already have. So you could do this, and then, assuming the internet is okay today, it will pop up, and yes, it'll say some other things that I have working on. I don't actually recall starting that notebook, but sure, whatever. You can create new worksheets and stuff like that, and you can manage it all in the cloud. This way you don't have to worry about maintaining your own installation until you're sure you really want to play around with this. But I'll go back to the one that I'm hosting locally. So the notebook, there's really only a couple things I want to say about it. I mean, it's just got your basic standard sort of features that you can save things, you can evaluate cells, you can get the actual text and stuff like that. It's pretty easy and pretty self-explanatory, and I don't need to read it to you on what these things do. So I think it was meant to mimic the Mathematica Notebook, if you're ever familiar with that, and it is now sort of also like the IPython GUIs that are out there. IPython definitely Sage had a lot of influence on the way IPython was developed. And you do Shift-Enter to just evaluate things. And so let's just talk about what Sage adds to Python, because I assume we all at least know a little bit of Python. And you can do all your standard sort of Python stuff, Essentially, you could just treat this exactly like just, your IPython GUI in some sense. There are a few things that are different, though. So Sage, for one thing, they decided in order to be more mathy, they wanted to take the caret operator and make it, instead of being XOR, make it exponentiation. Because this is a more mathy way to think about things. And so now they have double XOR is now XOR. So, that should be 2 to the 1 and 2 XOR 1, respectively, right? There's also some other things going on. That is accomplished via using a preparser rather than actually rewriting all of Python. They just have a specific function they call. And it does a few other things, too. For instance, it rewrites what numbers really are. Like, normally, if you look at a number, if you look at the type of a number in Python, you get an int. But in Sage, you actually get an integer. And this allows you to do some really cool things. At first, this may not make any sense, because in some sense, it slows things down, since this weird, sage.rings.integer object is kind of weird, but it has a lot of stuff that comes with it. For instance, you can call functions directly on it in a way that you could in, say, Ruby, but not in Python previously. And I can just, do a whole bunch of other things like for.abs, right? And that will just work, right? So you get some nice little features from that. You can also just start inputting in polynomials or expressions just directly in, and they'll just sort of work. So solve is a function that's very important if you're wanting to solve equations and whatnot. So you can ask Sage to solve an equation right there. Solve is built in, and it will assume that you meant that to be some sort of integer or complex number. It's sort of vague on exactly what x means at that point, but I'll get into that in a bit. So you can also ask it to solve for an imaginary equations there. And you can ask it for help, just like in the normal interpreter. So, I want to know more about this solve thing, right? So I can do the standard sort of question mark, and it will give me all the doc string. And they tend to be very detailed doc strings in Sage. They put a lot of their tests in here, so you sort of see exactly like a lot of the edge cases and how it's used, and a lot of really good examples. Sage is really big on having great documentation. And another thing that they added on, I don't think this is necessarily available in other notebook-like things, but you can actually always ask for the source by using double question mark. So if you really want to get into what exactly the solve function is doing underneath the hood, you can ask for that, and it will actually tell you the source code. And you can go in, it's just a doc string up there, and then I don't know, for some reason it crashed, I guess, because it got too big. But you could go through and you could look at all of the source code, and it'll tell you where the source code is, so that if you have your source code around, you can see exactly what file that's in. So I think that's really neat. And let me know if there are any questions as I'm going. This is a little bit more informal, I think, than some talk. So just shout out a question and I'll repeat it if something I say doesn't make any sense, or something you have a concern about. I'm happy to answer. Right, so what else can we do? So maybe we want more than one variable. We want x and y. So we can easily declare a function. So the first thing there is the var function. It declares a variable, essentially. I want to say I'm going to have a variable, and it's going to be named y, and then I'm going to use the actual named thing y to manipulate it, right? And now you might ask yourself, what can I do with this, right? So this is really the power of Sage, in my opinion, is you can do normal tab completion. This is almost impossible in any other math environment that I know of, to have sensible tab completion. So you can I like to say, tab complete your way to freedom. Like, you may not even know what exactly the name of the function is you're looking for, but maybe you'll look through here and realize, oh, I really wanted to differentiate this. And then that's the verb I want, right? And then now, as long as you can type, it will differentiate it, right? So you can sit there and just sort of hunt and peck around math. Like, even if you're not, the most solid, you don't know exactly what you're doing, sometimes you can sort of just figure it out by looking through all the functions that are available on an object, and then playing around with them and reading the doc strings on them all. And this is what I love. So, so some other useful functions. So I think the end function is borrowed from Mathematica and a few others, where it'll give you the approximation of something, like numerical approximation. So if you have some monstrous number, you could ask it to print it out in decimal format. So that's kind of nice. And then it's got some really funky syntax that, unless you actually like Magma, you should probably just ignore this first line here, which I think looks terrible. And what essentially this is doing is saying that you want this variable x to be an integer polynomial generator kind of thing. A much more simple way to say that is x equals polygen zz. And in this case, those are essentially equivalent expressions. This first thing is pre-parsed to be, make sense, because it looks sort of like some Magma syntax. The original developer, William Stein, was really into Magma before he did this. So it borrows a lot of influence from Magma, actually. There are a few other ways to actually do this exact same thing. There's I believe it's, you can declare, this is sort of like a more mathy syntax, where you have, zz is your integers, and you can declare x to be a variable in the polynomial ring. Anyways, I'm going to try to avoid too much, mathiness. But so another really neat feature of Sage, though, is the Scytheon, and this is integrated even in the notebook. So let's talk about Scytheon. So, I'll do the standard sort of example that I think everybody sees whenever they first learn Scytheon, which is you have this really slow add function, right? This is just your sort of standard Python loop, sum up all the squares of numbers or something like that, right? Something that, isn't really that slow, but it's slow enough to demonstrate. Well, in the Sage notebook, you can actually inline Scytheon code, and it will compile it right then and there for you. So you just annotate it with this sort of %Scytheon, and then you write normal Scytheon code, which, if you don't know, is essentially Python code, but you annotate it with some types. You want to say that m is going to be not a Python integer or a Sage integer, but like a machine integer, so that it can do really fast arithmetic. right? And ditto with I and S in this. And this is essentially the same code. You're just saying that we pinky swear that we're not going to exceed machine precision when we do this, right? And it will let you, be stupid about it too. So it's going to take, it takes a couple seconds because it has to find my C compiler and everything. And it generates the Scytheon, C files in the background. But now I should be able to do, slow add and fast add. And yeah, of course they get slightly different answers because it's exceeding machine precision. I think if I did, maybe up to 1,000, it would probably be the same. Yeah, there we go. And so you might ask yourself, well, of course, if you've never seen Scytheon before, then it might be neat to know exactly, what really happened there. So we can see that this slow add originally took 12 milliseconds to execute, which doesn't seem so bad until you realize what a compiled C version does, which is about 1,000 times faster. So, and it's neat, and Sage is neat because you can play around with the Scytheon without actually, having to be at a command line prompt and compiling it all yourself. So, if you're really into Scytheon, you can ignore all the math junk and just play around with Scytheon in the notebook, and I think that's pretty cool. So I think I'll move on to plotting now. So another really neat feature of Sage, I think, is being able to inline plots. So, a lot of this functionality is available in libraries like Matplotlib and Pylab and stuff like that. And this is exactly actually what Sage is calling in the background. But, it integrates these pretty well so that they just sort of pop up in the middle, here. You can just say plot x squared minus y. You don't even say what x is necessarily. It just sort of knows you probably meant to plot it and, you wanted to look at a picture that looks something like that, right? I think that's pretty neat. So, if you only wanted to do even basic sorts of, algebra and plotting, that's nice. You can also do 3D plots. This will probably take a couple seconds to load up because it has to call, I think JMol is the library that renders 3D stuff for it. So yeah, it's some Java thing, I think. So, you can do the standard sorts of plots that you expect to do in a math program. But we're in Python, so we can do more. So, the actual, whenever you plot something, you actually get an object, right? Like, you can assign it to a variable, right? And then it has, some methods and, right? There's all sorts of things you can do to it. And you can, and so, they also decided to override operators so that, if you add two plots together, it does exactly what you'd expect. It plots them both at the same time, right? Rather than having some really annoying syntax for trying to, plot multiple things at the same time. And it supports keyword arguments to do a whole bunch of fancy things like change the way the lines are drawn or change their color. And they behave exactly how you'd expect. And there's lots of great documentation in the plot function itself that can tell you more. So, in addition to that, that normally is meant for plotting actual functions or expressions. You can also plot lists of data. So this assumes that it's sort of one-up indexing of data, or zero-up, I guess. And it will plot it, as dots. And again, a whole bunch of keyword arguments are supported. Bar chart, similar, except for it creates a bar chart. And there's half a dozen other of these, right? Doing all the sorts of things you'd want to do. So I like to give real world examples of how I actually use this in my life. So I, in my spare time, work on some common libraries that do things like implement sets using hash tables and stuff like that. And we care a lot about efficiency. And so it came up recently where we wanted to have a hash table that had that was filled up to a certain amount. And so we spent some time and we worked out the math to figure out exactly the formula for what this what this looked like. And I wrote that here. So I want to have three variables essentially. And I have a fixed, what this is called a load factor of your hash table, which means essentially how full is it. One would be completely full and then 0.75 is not at all. And we want to know exactly if we put things in this, essentially it's like a Python dictionary or a Python set. If we, fill it up, how full is it really going to be, if we have hash collisions and all that kind of stuff. And it turns out this is the right formula. At least I really hope it is. And I'll say that essentially if you have 100 slots and you want it to be filled up to 0.75, how many actual unique hash codes are you going to see probabilistically? And the answer is about 72 or 73, right? I mean, you're going to have about 2 to 3 collisions, which is pretty reasonable. But one of my colleagues noticed that this looks like that this function here is, for one thing, awfully complicated, and we want to be able to compute it on the fly. So maybe it actually isn't that complicated. And it turns out this is what it looks like when you plot it. So you're like, I wonder if we can just ask something to give us a linear regression on this and avoid all those expensive exponentiations and logarithms that have really poor performance. And if you zoom in right here, it looks really different near the origin, but really it is a line. So Sage supports this. You can essentially generate data. So we had that function from earlier, which is essentially generates how full the hash table is. And I want to generate, maybe we only care for up to size 1,000. Maybe beyond 1,000 we don't care so much. So what you can do in Sage is you can declare a model, which essentially this part is saying this is a variable in X, and those other things are sort of constants. And then there's a find fit function, which does a linear regression. Essentially it finds the best line, right? So we can do this. It takes like a second or so on this, and it'll tell you, yes, and given this model, if you give it these coefficients, then you will have a line that should match that as closely as we can. And so just really quickly, I'll plot both of them together. And you can see they match perfectly, right? So that's actually what we're going to use in the code, is because why do all that exponentiation and stuff whenever we can just do that? So real world example. And I'm going to go into another real world example. That's going to move past plotting. So if there are any quick plotting questions, I can address those now, or otherwise I'll just move on. Yes, if you can come up to a mic, that'd be good, or just shout.
Can you zoom in on any of the plots?
Sure, so I don't think you can just like zoom in, because this is actually like a PNG, but you can zoom in by just changing the range here. So like if I want 0.0 to 0.5, right, then it will, so it's not quite as nice as some other packages, which you can like use your scroll wheel to zoom in, but put in a bug request for that or a feature request, and I'm sure that they can work on that if that's a really killer feature. But okay, I'll move on, and then we can come back to more questions on this later. So another colleague of mine had a question. We were doing some math work, and he had a question about the way CRC works. And so sort of to prove, like, CRC math looks kind of mysterious if you don't know a whole lot about, algebra, and you've never really looked at this very much. And so I wanted to just demonstrate that, this stuff really does work. And I also like to sort of see this sort of thing myself. I'm actually a computer scientist primarily, so occasionally I like to actually look at my math and play around with it to, prove to myself that it really does work. And so all I'm doing here at the beginning is I'm just going to say that now, instead of working in integers or real numbers or complex numbers, we're going to work in binary numbers. And we're all done some programming, so hopefully we know sort of what binary is. Essentially, this means that we can have polynomials, and instead of addition and subtraction, you just have XOR, right? So just to verify that, x times x is still x squared, but x plus x is 0, because they sort of cancel each other out, because addition is the same as XOR. And it operates sort of the natural way you would think it would on polynomials, in that x is going to cancel itself out via XOR, right? If you don't follow this completely, that's fine. I'll move through it kind of quickly. So if you ever look at the way CRC works, you want a certain kind of polynomial, which is sort of like the error checking polynomial in CRC. And the question that my colleague had involved whether or not you could just like remove bits from this and it still works. And I said, no. This is, if you want a smaller polynomial, then you should do something like this. Right? So this will quickly find a CRC-like polynomial that can be used to generate these checksums. So the actual value here doesn't really matter too much. And there's a whole bunch of these. It will just start randomly picking out some. And then to sort of prove to ourselves that it works, what I can do here is I wrote a really quick function that turns any string into a polynomial. This is essentially what CRC does. It treats strings like polynomials. This looks kind of ugly in Python, but at like the actual bit level, this is really, this is like a trivial operation, right? So you can just sort of ignore that and know that if you have like some little string here that, you can sort of see how the ones map to x, there's 1, and there's x cubed, and there's x to the 6th. And you can, ask it to just take a string, and it will output some god-awful long polynomial, right? And just to sort of prove to us that, this really is doing it here. So one of the keys of CRCs is that you can concatenate things. And this is sort of the way you do it, is that you can take your polynomial, for half of that string, multiply it by some constant, and then add in the next polynomial, and you should get the same thing. And if you looked, you can tell that they basically are the same thing. And CRCs are all about taking that original polynomial and modding out by it. And that would be your CRC checksum, right? And so the question that he had was, how does this sort of commute? So I can take, essentially modding out by the polynomial here, then multiplying in by this sort of addition, or this scaling factor here, and, modding out by the polynomial as much as I want, and it doesn't really have an effect on it. This should be the same thing as this, and it is. And so the real key, though, is that, if I already had a checksum for the spaghetti part, and I then calculated separately the checksum of sandwich, can I combine them to get the checksum for spaghetti sandwich? And you can, which I shouldn't say proved, I demonstrated there. So this is sort of to help out my colleague and make sure that hopefully he understood, and hopefully this wasn't more confusing to him. I found this more enlightening. And it's always fun for me to play around with the math. Hope that makes sense. This is a really long example that I don't want to go into because, time is not working out for me here. But essentially, there's some really cool other algebra stuff you can do. I want to talk a little bit about number theory before anything, because some people really like number theory. You can do all the sort of standard Python stuff. You have modulus. You can also, there's built-in functions to deal with things with number theory, like there's a primes function, so you can have it print out all of the primes up to 40, right? So that can be kind of handy, so you don't have to keep figuring out over and over again how you generate all the primes between 2 and whatever you want. It already has that built in. These numbers do support all these nice fancy functions we talked about. Like you can give it 2012 and ask it, is this prime? And if you know it's not prime, then you know that you can factor it into other things. And factor is a really neat function. There's this cute little command line argument, verbose, where you can have it explain all the gory details of what it's really doing under the hood when it's factoring. And I'm not going to go into these, but if you ever get bored, I look through the verbose section and just try to figure out what's going on. It's kind of fun. You can also do the standard, I have a prime or I have a number and I want to know the next prime up. If you're doing some sort of iteration over primes, that can be useful. Other number theory, Chinese remainder theorem, if you don't know what that is, that's fine, but it has the built-in Chinese remainder theorem function. Essentially what this means is it finds a function so that it essentially gives you this number so that it's equivalent to 12 mod, or 12 mod 17 and 3 mod 31, which is a terribly sort of, that's obviously not clear what it is, but the doctrine goes into detail. If you want to, and obviously Sage extends this to all sorts of other things. If you really want to play with algebra and stuff like that, you might be interested in doing, for instance, if you look at complex numbers, the number 2 is no longer really prime, right? Or these are actually the Gaussian integers. 2 actually can be factored, and it'll tell you what the factors are. If you take I times, or minus I times I plus 1 squared, you'll actually get 2, right? So it can do all sorts of, other math in other fields. And it can do, so I'll talk very quickly about matrices because I'm just about out of time. But you can do matrix stuff too. So you can generate a random matrix. You can do linear algebra on it, like solving for a right null vector. You can multiply that and you can verify that you actually get the original thing you were looking for. You can ask it for determinants, transposes, inverses, and if you take m times its inverse, you sort of get the identity matrix. There's some precision problems as always. And I was going to show this nice little power grid demo, which I'll go ahead and do really fast. This is sort of like a power grid map, which is a board game. Essentially, you can do some quick graph theory on this. I'll just skip through this really fast. Essentially, you can make a graph and it will just display it inline, right? And so if you want to do some graph theory on it, like the Kruskal algorithm implements a minimum spanning tree, which is sort of like playing the game of Power Grid optimally if you've ever played it. So it'll tell you exactly how to play Power Grid, right? I think that's neat. That's all I think I had, and I'm just about out of time, except for, so we have time for questions now, about 5 minutes, I think, so I would be happy to talk more. So please come up and...
Yeah, we do have 5 minutes for questions. I'd urge everyone to come up to the microphone and ask them.
I'll just go this.
Yeah, this looks very similar to the IPython notebook interface that we have seen today in the other talk. Can you highlight what are the differences between Sage and IPython?
A little bit. So the question was, I like to repeat the questions. What are the differences really between this and the new IPython GUI that came out with 0.12, I think it was, recently? So actually there was a really great blog post on the IPython blog that went into great detail on exactly why it took IPython so long to go into to do this, and how they sort of took a lot of inspiration from the Sage Notebook to build theirs. The differences are, so the Sage Notebook obviously integrates in a lot of graphical features, like being able to plot things in line and being able to, like compile Scytheon in line and whatnot. And I think there's also some data differences as well. I believe IPython still tries to maintain its sort of like command shell replacement utility, so you can still like CD around and do stuff. I think you can do this in Sage, but it doesn't work quite the same. Like I'm not sure if that makes sense anymore. Yeah, so this doesn't make sense in Sage Notebook. I think you could do that in the IPython GUI though. You'd have to ask those guys. So I believe IPython did take a lot of influence from this, but they sort of fixed what they saw as problems in this. But again, I'm not an expert. There is that really great blog post, and if you're really interested in the differences, I'd encourage you to read it.
So this is great for interactive use, but can you then take what you type in and make a script out of it, say, without doing the plotting?
So yeah, I think so. Up at the very top, there you can save it for one thing, and I think there's also this text button here, which will sort of give you an interactive session that you got out of it. I'm not sure. I think this just is embedding the help and whatnot. But I think you could turn this into a script fairly easily. I'm not sure what the publish is not what I want to do. That makes it where other people can get to it. But yeah, so you can, I think using the text one, you could probably write a quick script to pull out the beginning of it. I don't think there's a way to export it natively into a script, because this is sort of viewed as, a script itself. And I think most people who use Sage probably interact with it through the notebook more than they do the command line. Although I do have a command line running, you can do all the things that I was doing there, right? Right, whatever. Okay, any other questions? Yes?
Can it do, say, hard integrals like elliptic integrals?
Yeah, I believe it has all the full, I didn't talk much about calculus because I find calculus really boring, but I'm sure it has, okay, well, I don't actually know what all that stuff does. It certainly has integrals, wait, was there? Okay. Okay, I'll take your word that one of these things might be an elliptic integral. But yeah, I fall asleep whenever people start talking about, line integrals and things like that. So, but there are lots of great calculus and differential equations features out there as well.
Great, Chris, thank you very much.
Thank you.